Stop.
But it's funny, I was talking to somebody from New York State.
All right.
And they make
Test 1, 2.
they're saying there is you should bond your equipment to the physical ground, frame of the building or something like that. Everything's going to go there, but they're saying don't use this. This is a neutral wire. So this is grounded here, and we can ground stuff past the ground point, but this is dedicated here because current's going to flow through these phases back to ground. So we shouldn't use that for equipment bonding. That's the white wire, neutral.
And you're grounding your equipment because it can build up a charge.
You're grounding your equipment for safety because if you had, well, let's just say this is the inside of a transformer, right? It is, it's the inside of a transformer. And you don't bond the outside metal box. If this wire comes loose and touches that box and it's not got a bonded ground, current won't flow and it won't blow the breaker, which means if somebody touches it, they'll become the breaker or fuse, whatever you want to call it. And notice there is a grounding right here. I don't really like that. That grounding diagram should, this little symbol here, in my opinion, should be back here. Kind of confusing. There shouldn't be an earth ground before we get back to our neutral distribution. Typically, you'll see them tied at the same place right here, but not out there in the field. Because what we want is we want everything to come back here, close to the transformer, and go to ground. So on some delta systems, one of the phases is center tapped and grounded, and this becomes the neutral for the system and provides several voltage options. The 240 volt AC phase-to-phase voltage is still available. However, a single phase 120 volt AC is available between phase A and neutral and between phase C and neutral. So if we look right here, we'll see this. Now, here, between this, and yes, that says the word bastard voltage. That is commonly what it is referred to and has been for a long time. I didn't make it up, it's right there. This voltage here on a transformer, they use that sometimes, and what they use it for is lighting. Stuff that can, and typically you're not going to use a lot of your ballast in your fluorescent lighting were able to handle that, and that's all they used it for. Certainly don't want to plug your computer into it. And it says, note, NEC 10-15, high leg marking requires the high leg to be identified by orange color for this configuration. Typically, people don't really, I don't think I've ever seen anybody use it, but you could if you wanted to. Mainly because if you run 190 volts in the plant somewhere, somebody's going to make the mistake of sticking a breaker on that panel and trying to plug up something. Trying to plug in off of it, it'll be bad.
If you don't use it, are you wasting anything?
No.
Okay.
This is distribution transformer. Remember the transformer we went and looked back in there? That's supplying the 3-phase to the classroom. So here we have a skill. We're going to use a voltmeter to verify supply voltage. And we have a simulator. We'll just do this on the screen up here real quick. Here in a little bit, we'll have you put on your art glass, and you can do it for real since we have the equipment. So typically what we're going to do is we're going to go through here, and we're going to locate the test probes. We're going to connect them here, here, and have a diagram here somewhere. Segment 3. Okay. We're going to remove our lockout. Now we have power right here. We can come over here. We're going to put this on 600 volt AC. We're going to come over here. Typical disconnect. You want to check to ground, which will be our neutral, and see what we have here. We have 120 volts. Here we have 120 volts. Here we have 120 volts. That tells me that I have all three legs of this circuit. This is 220. This is what we have in the classroom. If I check between them, I should read 200, well, 208. If I check here, you'll notice when people get to talk about 220 or 208, they kind of just run them together. If not, they don't distinguish too much. All right, so we've done that. Guess we shouldn't have closed that window.
I do that all the time.
So a grounded system includes a grounded neutral conductor and the three-phase feeds. An ungrounded system has only the three-phase feeds and does not include a neutral. So what they mean by that is the center tap is not here. They're not tapping off here to give me a neutral for this configuration. You see that? If I'm not going to run 120 volts off this transformer or whatever it is, I don't need that. All I'm using is three-phase power. I wouldn't need a neutral. Three-phase motors do not have a neutral. They have a ground wire and then the three phases. For example, we may have said this earlier, but in your typical three-phase system, you have each phase here. As this set of windings in the motor begins to get fully attracted, it's causing this rotating magnetic field. As that rotation drops, the next set of windings are wired to this phase and they pick it up. And so you get more efficient motor. In a 120 volt system or single phase, you only have one hump to do the power, right? That's all I got. And then I got to wait till it gets all the way down here before I have maximum power that I can achieve anything with. So you have this big gap. That's why we have three phases in the first place. More efficient. So if a ground fault occurs on one of the phases of a grounded system, the circuit protection devices will open, and because of this, increased current will draw and will cause the system to shut down. Remember, these are the symbols right here on an ungrounded system. That's, I mean, I guess you could say that, but on a three-phase system, you do have an earth ground. So here's our earth ground over here. When it talks about one of the advantages of a grounded system is that any of the three phases can supply single phase power by connecting here and here. They're all going to this neutral wire right here. See that? So we can tap off of here and get 120 volts. So this talks about large manufacturing facilities often use ungrounded delta system. This system is desirable in these applications because it can continue to operate if one of the phases is lost. However, most plants are running close to their max potential, so they're going to shut down if they lose a phase regardless. The rest aren't going to be able to keep up. But that's, your book says otherwise, so. One problem with ungrounded delta system is that a phase winding can become grounded accidentally without anyone being aware of it, and this can result in somebody getting shocked. If we ground it, see, here's ungrounded, here's grounded, he's not getting shocked. The current is going to follow the path of least resistance. This talks about a large facility installing fault indicators to let them know when a phase is grounded. And those are just simply indicator lights or indicator devices. They're probably going to be good. Most of this would be located in a room nobody goes in. So a light's not going to do you any good. It needs to be an email device, digital device, or a horn or something.
Even on your SCADA system, sometimes going to. Even on the SCADA system control room.
Yeah.
They'll show up.
Yeah. Need some kind of signal to notify somebody. HMI or SCADA system.
Orange good.
Orange good. So, all that's white right there. We're going to just talk about, we'll see if they get to it on the next one. If they don't, we're going to talk about how to change direction of a three-phase motor. That should be coming up, I hope. You're going to do that today. So let's talk about disconnect devices. We have fusible disconnects, as in this is a disconnect with 3 fuses. We'll drag out one, I'll put it in front of the camera. You guys can go up there on the trainers and you can actually see one, but put it in front of the camera. That sounds like a good time for me to cut that video out and make a separate small video out of that. So I got everything set up. We have circuit breakers. That is a two-pole breaker. Typically, you're going to see them with 3. And so we have skill 3, which you're going to do. We're going to use a digital multimeter to check the condition of a fuse. So let me walk you through it on the screen, and then let's do it for real. How's that sound? So perform the following substeps to prepare the digital multimeter to measure AC. Locate the meter, test probe. We're going to put our probes in there. We're going to set it to ohms, probably 200 ohms. First thing we need to do is click this. It is off. We need to isolate that. We're going to lock it out in 2 places, I guess. We're going to see if we can't get this open. This one's kind of tricky. All right, maybe we didn't go there. So click the center of the station to remove. Up position. Let's put it back in there. All right, so first thing they want us to do is measure voltage from L1 fuse to the load side, as shown in graphic 2. So they want us to open this up and look at it. So putting it on ohms is not correct. We'll put it on 600 volts AC. We're gonna open the door. Open sesame.
Just click on it. Click on the door. Just on the right part. Just click on it. Should open. Right above safety. Somewhere. I did it out there.
Thank you, door.
Maybe it needs to be locked and then open and unlock.
There we go. All right, here we go. Now we've got power. And so in graphic 2, they want us to check each one of it, L1 to L2 load side. So we're going to check here. They're going crisscross, checking each fuse. And we're reading 208. All right, we're going to check from here to here. We still have 208. Whack open. From here to here, and we have 120 volts. All right. What do you notice different? We should be reading 220 across it. It's turned off. 208 across here. We read 208 across here. Come over here. All right. Measure the voltage from the line side of L2 to L3 shown in the graphic 3. So look at graphic 3. So they want us to go through here like this. They're actually touching on the blade here. So let's see. Let me go on there. Measure the voltage from, record that, measure the voltage from line side of L3.
So you might have lost a phase.
We're going to do the cross check. Well, they talk about the cross check method, which is right here.
Yeah.
So it says this is what they want you to do. Measure voltage from line side of L1 to load side of L2 fuse. So line side of L1 to load side of L2 fuse. The load side is on the bottom. Electricity comes in the top and always goes out the bottom of these devices. And then it says measure voltage from the line side of L2 fuse to the load side of L1 fuse. It's got a little chart here that I'm going by. You can print out. It's on your. We're reading 120 volts. It says low or 0 volts indicates L2 fuse bad. Line voltage indicates L2 fuse good.
So what the line voltage? 208.
Well, it should be reading 208 there, I would say.
Yeah, I would say too. The fuse is not doing anything.
So I would say they have a little glitch right there, but here we'll see about just setting it up and doing it for real with my yeah. That should be reading 220. Do you agree?
Yeah, I agree.
That should be reading 200. maybe, oh, wait a minute.
There
There we go.
Oh,
Never mind.
why not?
There we go. We turned it back on. That's right. And so what they're trying to do is, we know there's no fuse over here. And if we check to this one,
Yeah.
we're reading 220 or 208. And then we're going to move down over here and check to here. We're reading 220. If we check to ground, it won't let me go to ground. But if we check to ground, we should be reading 120 volts on each one of these legs. Let me do that. So it goes through there and it talks about doing a cross check to determine if all the fuses are good. Now, the second part of this activity is to lock this thing out and check a fuse. We're going to own the fuse. First thing we want to do, I know why I made all these pictures in my diagram because it's confusing. And so here we're going to apply the lock and check the fuse. And there's a picture in the conductive course. So we're going to turn the power off. We got the door open. Power's off. Get rid of that stuff. We want to disconnect the power. Typically, I'm going to be honest with you, you're not going to have a three-phase outlet. That's not going to be there. But we're going to go through here and do what they want. And it's a twist lock, so you have to turn it. And then it wants you to make sure you lock it out. Typically, your lockout is not going to be in this disconnect. It's going to be somewhere else. But actually, in this room, we do have twist locks. So in this room, we'd actually perform these steps. And we need to, okay, we're going to drop that in there. That's how that works. We're going to drop that in there. We're going to seal it up. We're going to apply the lock. We're going to get our fuse pullers. Now, the reason we use fuse pullers is we don't want to damage these, okay? But in the real world, you'll see people pry them out, grab them with channel locks and everything else. The important part before we do anything else right now is to come over here and make sure that it really is off. Because this is where you can get shocked pretty bad. These are line side. This is high amperage. It's probably got 100 amp service. So it is off, so it's safe to grab. We're going to come over here and
Close the door.
yeah, close the door. We're trying to grab a fuse, and if you do it just right, you're supposed to be able to grab a fuse out of here. Come on. I gotta make a video of this somewhere else. All right, well, we grab a fuse and pull it out, but that's not working. So let's just assume we pulled the fuse out. And we'll switch camera angles here. See if we can find one of these. Come loose these. We got one right here. How about we just do it for real? The virtual is good. There's really no substitute for the real thing. It's really close. Here's our disconnect. This is already, we don't have to worry about this. I have this disconnected. So we're going to open it up. Notice that inside this disconnector are fuses. And if you look right here is a blade. Let's see if we can do a little autofocus here. You'll see a blade right here. And that blade is controlled by this handle. See the switching action of that blade? That switching action, and you'll see some little lubricants. If those don't engage correctly, that's going to cause an overload when we try to fire this up. But we're going to pull a fuse out and test it. I locate my fuse cord. After having to talk about channel locks on my fuse cord, which I had out like yesterday. That's not. I was pulling fuses yesterday with it. That blue handle fuse puller laying somewhere. Here's my electric properly. Over that. Same place I always put it when I'm looking for it.
Yeah.
All right. Note to self, we've got to cut this video down and post it. Cut this part out. All right, so we're going to take our fuse puller. Notice it is plastic. We're going to come in here and we're going to pull this fuse out. Grab it. This should be bolted, but I'm going to have to hold it down and pull straight out. It should come right out. Now we're going to come over here. We've got our fuse. We're going to turn our meter to ohms. First thing we're going to do is check our meter to make sure that it is functioning. And yes, it is. We're going to take the leads. One of the things you need to watch out for is on an auto range meter, you will get a reading if I just hold it in my fingers, right? I'm getting mega ohms. That's no good. That is the resistance of my body right now. So you need to pay attention to the number. You should be down here on the ohms level. So or the not on kilo ohms or mega ohms, or just on ohms. And so that fuse is good. If we pulled it out and it didn't test out, so I'm grabbing this fuse and I'm holding nice steady pressure, and I see that says kilo ohms. That fuse is partially blown or is entirely blown. I don't know why it's not all the way open. We can check another one here. I have a large quantity of blown fuses. See what that one says. That says kilo ohms too. But if I touch my fingers to it, you got to be careful that you don't actually read the resistance of your body. This should be like 0. This should be just like a solid wire. All right, and so now it's your turn. Go get your meters. I'm going to pause the audio and video